Transient heat conduction. This topic discusses transient heat conduction, where the temperature inside a body changes with time. Unlike steady-state conditions, the temperature distribution is not yet stable and continues to evolve. This phenomenon is crucial in real heating and cooling processes, such as quenching or component cooling. The analysis requires understanding material thermal properties and heat transfer mechanisms. This chapter provides the foundation for understanding how systems respond to changing environments.
Lesson Plan: Heat Transfer. This slide shows the position of transient conduction within the overall heat transfer course structure. The chapter sequence is designed so students master the basics before moving to more complex analyses. Transient conduction is built on the understanding of steady conduction and the heat conduction equation. The following chapters extend these ideas to convection and radiation. With this structure, the learning flow becomes systematic and well-connected. Learning outcome. The learning outcomes emphasize the ability to choose the appropriate method for transient conduction problems. Students are expected to distinguish when the lumped system approach is applicable and when it is not. In addition, analytical solutions for different geometries are a major focus. The concepts of semi-infinite media and multidimensional solutions are also introduced. Overall, the outcomes are oriented toward analytical and modeling skills.
Lumped versus distributed temperature. This concept compares two extreme cases of temperature distribution inside a body. In a lumped system, the temperature is assumed uniform throughout the body and changes only with time. In a distributed system, significant temperature gradients exist inside the material. This difference determines the complexity of the model that must be used. Choosing the correct assumption is critical for obtaining accurate and efficient results.
Parameters in lumped system analysis. The lumped system analysis is based on the physical properties of the body, such as mass, volume, and initial temperature. In addition, surface heat transfer by convection plays a central role. The body temperature is assumed uniform and only a function of time. This greatly simplifies the energy balance equation. However, this simplification is valid only when the physical conditions are satisfied.
Temperature behavior in lumped systems. The temperature change in a lumped system follows an exponential trend with time. At the beginning of the process, the temperature difference is large, so the heat transfer rate is high. As time progresses, the body temperature approaches the ambient temperature asymptotically. The parameter B controls how fast the system reaches equilibrium. This behavior reflects the assumption of no internal temperature gradients. Temperature decreases exponentially over time, reflecting lumped system assumptions. Heat transfer in lumped systems. At the beginning of the process, the heat transfer rate is at its maximum because the temperature difference is the largest. As time passes, the temperature difference decreases, and the heat transfer rate also decreases. At the final condition, the body temperature equals the ambient temperature, and heat transfer stops. The total heat transferred can be calculated from mc Ti minus T infinity. This concept is very useful for estimating simple heating or cooling times. Contributions of Jean-Baptiste Biot. Jean-Baptiste Biot made important contributions to the development of heat conduction analysis. His name is preserved in the Biot number, which is crucial in transient conduction analysis. This number relates the surface convection resistance to the internal conduction resistance. In addition, Biot is also known for the Biot-Savart law in electromagnetics. His contributions show the strong connection between physics and engineering. The Biot number and heat transfer. The Biot number is used to assess whether internal temperature gradients can be neglected or not.
If the Bi value is small, the internal conduction resistance is much smaller than the convection resistance. In this condition, the lumped system assumption is valid and safe to use. If the Bi value is large, internal temperature gradients are significant and a distributed analysis is required. Therefore, the Biot number becomes the main criterion for model selection. Lumped system criterion for copper ball. A small copper ball is an ideal example for the lumped system approach because of its very high thermal conductivity. With high conductivity, temperature gradients inside the ball become very small. A Biot number much smaller than 1 indicates that internal conduction resistance can be neglected. The small geometric size also helps the temperature become uniform throughout the volume. This combination of material properties and size makes the uniform temperature assumption very reasonable. The answer is answer B. High thermal conductivity ensures negligible internal temperature gradients within the ball. Explanation of incorrect answers. A. Incorrect. A Biot number below 1, not exceeding 1, confirms the lumped system is valid. C. Incorrect. Heat conduction is essential for uniform temperature. Preventing conduction contradicts the analysis assumption. D. Incorrect. Small size, not large size, combined with high thermal conductivity, ensures uniform temperature distribution. Heat transfer analogy with island traffic. The island analogy is used to simplify the understanding of convection and conduction roles. Boats arriving at the island represent convection, bringing heat to the surface. Buses inside the island represent conduction, distributing heat throughout the interior. If boats arrive quickly but buses move slowly, heat will accumulate near the surface. The balance between these two mechanisms determines the heating or cooling rate of the object. High convection and low conductivity. When the convection coefficient is very high, but the material conductivity is low, the internal temperature gradient becomes very large. Heat can be transferred very quickly at the surface, but has difficulty spreading into the interior. As a result, the outer region can cool or heat much faster than the inside. This condition requires a distributed conduction analysis rather than a lumped system. The choice of material and convection conditions becomes a critical design factor. Plate temperature versus air velocity. This graph shows that the plate temperature decreases as the cooling air velocity increases. Increasing air velocity raises the convection coefficient, which enhances the heat removal rate. However, the temperature reduction is not linear and eventually approaches a minimum value. This indicates a practical limit to cooling performance improvement by increasing airspeed. From an engineering perspective, there is always a trade-off between performance and fan or blower energy consumption. One-dimensional heat transfer geometries. In these 3 geometries, the initial condition is usually a uniform temperature throughout the body. After that, heat transfer occurs by convection at the surface. Because of symmetry, the temperature variation needs to be analyzed in only one spatial coordinate. This approach significantly reduces mathematical complexity. This is the basis of many classical analytical solutions of transient conduction. Heat conduction in a sphere is radial, with varying temperatures from center to surface. Transient temperature profiles in a wall. At the beginning of the process, the entire wall has a uniform temperature. When cooling starts, the surface cools first while the interior remains hot. As time passes, the temperature profile inside the wall becomes more uniform. After a very long time, the entire wall reaches the ambient temperature. This process illustrates the gradual diffusion of heat from the surface into the interior. Benefits of non-dimensionalization. Non-dimensionalization is used to simplify the form of equations and reduce the number of independent variables. By using dimensionless parameters, the solution can be applied to many different physical cases. This approach also makes it easier to present results in the form of general charts. In addition, the influence of each physical parameter becomes clearer. This is why the Biot and Fourier numbers are so important in transient conduction analysis. Key observations on series solution. Analytical solutions of transient conduction are often expressed as infinite series. However, the higher-order terms decay very rapidly due to the exponential factor. As a result, the first term usually provides a very good approximation. The accuracy of the solution is influenced by the Biot number, position, and time. This is why the one-term approximation is very popular in engineering. Transient conduction solutions. This slide emphasizes that transient conduction solutions strongly depend on the geometry of the body. Dimensionless temperature is used to unify different cases within one analytical framework. Each geometry has different eigenvalue roots. Plane walls use trigonometric functions, while cylinders and spheres use Bessel functions. All solutions are still linked by the role of the Biot number as the connection between convection and conduction. The answer: A. Cylindrical and spherical solutions use Bessel functions due to radial symmetry, while plane walls use trigonometric functions. Explanation of incorrect answers. B. Incorrect. Convection is considered for all geometries, with the Biot number linking surface convection and internal conduction. C. Incorrect. Solutions for all geometries depend on the Biot number, but are not limited to high values. D. Incorrect. Temperature profiles in all geometries are influenced by Biot and Fourier numbers, which define the heat transfer behavior. Coefficients and functions. This slide explains the role of coefficients and special functions in transient conduction solutions. For plane walls, trigonometric functions are used, while for cylinders and spheres, Bessel functions are applied. The coefficient values change with the Biot number, reflecting the change in balance between convection and conduction. The geometric complexity is directly reflected in the mathematical form of the functions. This approach allows solutions that are both general and precise. Convection coefficient variations. The convection coefficient controls how effectively heat can be transferred between the surface and the environment. If its value is small, heat transfer is limited by convection, and the temperature gradient near the surface becomes large. If its value is large, the surface temperature approaches the ambient temperature. In practice, a finite value represents real conditions. The infinite case is used as a theoretical limit to simplify analysis. Fourier number insights. The Fourier number represents the ratio of heat conducted to the heat still stored in the body. Its value increases with time and decreases as the characteristic length becomes larger. This number essentially measures how far the transient process has progressed. If its value is large, the system is close to steady state. Therefore, the Fourier number is a very important dimensionless time parameter. The Fourier number represents the ratio of heat conducted to heat stored in a material over time. Semi-infinite body characteristics. A semi-infinite body is assumed to be so large that heat has not reached the deep interior during the time of interest. With this assumption, the temperature gradient is significant only near the surface. This greatly simplifies the mathematical solution of transient conduction. This approach is suitable for short-time surface heating or cooling problems. Many early-stage industrial heating processes can be modeled using this assumption. Transformation in heat conduction differential equation. By applying the chain rule, derivatives with respect to space and time can be expressed in terms of a new variable. This new variable is usually a combination of position and time. This approach reduces the number of independent variables that must be handled explicitly. The result is an equation that is simpler and easier to solve analytically. Error function characteristics. The error function naturally appears in transient conduction solutions for semi-infinite bodies. Mathematically, it originates from the integral of a decaying exponential function. Its value varies smoothly from 0 to 1 over the range of the dimensionless variable. In the context of heat transfer, this function describes how far the surface temperature influence has penetrated into the material. Therefore, the error function is very important in modeling transient heating and cooling. The answer: B. It simplifies solutions for transient heat conduction problems in semi-infinite bodies. Explanation of incorrect answers. A. Incorrect. The error function smoothly varies between 0 and 1, not -1 and 1, for dimensionless variables. C. Incorrect. The error function is the integral of an exponential decay function, not sinusoidal, and it is used in transient, not steady-state conduction. D. Incorrect. The error function is relevant for systems with conduction and convection, particularly in transient heat transfer problems. Dimensionless temperature distribution. Dimensionless temperature distribution is used to present results in a general form without being tied to specific units. For a semi-infinite body with constant surface temperature, the solution follows the complementary error function form. The temperature decreases with increasing distance from the surface and with time. This approach allows one graph or one equation to be used for many physical cases. This is the main strength of using dimensionless parameters in transient analysis. Complementary error function table. This table provides numerical values of the complementary error function for various values of the dimensionless variable. These values are very important for practical calculations without performing manual integration. When the required value is not listed, interpolation can be used. The table shows that the function value decreases as the variable increases. With this table, transient conduction analysis becomes much more efficient. Temperature variation in a large cast iron block. This slide illustrates various possible boundary conditions at the surface of a large body. If the surface temperature is specified, heat penetrates deeper with time. If the heat flux is specified, a surface temperature gradient forms and gradually spreads inward. If convection dominates, the temperature curve shape is strongly influenced by the convection coefficient. All cases show that deeper regions require more time to be affected by temperature changes. High thermal diffusivity ensures quicker heat penetration and broader temperature distribution. Temperature variation in semi-infinite solids. In a semi-infinite solid, the temperature is initially uniform and then changes due to convection at the surface. A higher convection coefficient causes faster cooling or heating near the surface. The temperature distribution is usually expressed in a dimensionless form to allow comparison across different times and positions. Deeper regions require more time to experience significant temperature changes. This behavior shows that transient processes are strongly influenced by both depth and time. Heat transfer between two semi-infinite solids with different initial temperatures come into contact. A temperature gradient immediately forms near the interface. Heat flows from the hotter body to the colder one until a local equilibrium is established at the interface. The interface temperature reaches an intermediate value determined by the thermal properties of both materials. Heat then propagates into each solid at a rate governed by their thermal diffusivities. The penetration depth increases with time on both sides. Temperature variation in wood and aluminum. Wood exhibits a very steep temperature gradient near the surface because of its low thermal conductivity. In contrast, aluminum maintains an almost uniform temperature throughout its depth due to its high thermal conductivity. This difference illustrates how material properties strongly control the temperature distribution pattern. In wood, heat penetrates slowly, so changes are confined near the surface. In aluminum, heat spreads quickly, causing the entire body to experience temperature change. The answer: A. Aluminum has higher thermal conductivity, enabling rapid heat distribution. Explanation of incorrect answers. B. Incorrect. Wood has lower thermal conductivity, leading to a steep temperature gradient near the surface, not uniform distribution. C. Incorrect. Aluminum does not reflect heat to maintain uniform temperature. It conducts heat rapidly due to its high thermal conductivity. D. Incorrect. Wood's steep temperature gradient is due to its lower thermal conductivity, not higher. Heat transfer in cylinders. In a long cylinder, heat transfer occurs mainly in the radial direction because axial temperature variations can be neglected. For a short cylinder, heat transfer becomes two-dimensional, involving both radial and axial directions. All exposed surfaces interact with the surroundings through convection. Geometric dimensions such as length and radius strongly affect the heat flow paths and rates. Therefore, the one-dimensional simplification is only valid for sufficiently long cylinders.
Short cylinder plane wall intersection. A short cylinder can be viewed as a combination of a cylindrical geometry and a plane wall. Heat transfer occurs through both the curved surface of the cylinder and the flat surface. Therefore, the problem can no longer be simplified to a one-dimensional case. An accurate analysis must consider both radial and axial directions simultaneously. This case illustrates how complex geometry requires a multidimensional approach. Rectangular bar in plane wall. A rectangular solid bar can be formed at the intersection of two plane walls. Heat flows not only within the bar, but also through the adjoining walls. The thermal properties and boundary conditions of the walls strongly influence the temperature distribution in the bar. The heat flow in this case is multidimensional and coupled. As a result, the solution is much more complex than that of simple one-dimensional geometries. The answer: A. The thermal properties and boundary conditions of the plane walls. Explanation of incorrect answers. B. Incorrect. While the dimensions of the bar affect conduction, the plane wall's thermal properties and boundary conditions also play a crucial role. C. Incorrect. Heat transfer involves both the bar and the adjoining walls, as they interact thermally. D. Incorrect. Multidirectional conduction is critical in this geometry, due to heat flowing in multiple directions through the bar and walls. The reference is from Yunus A. Chengel and Afshin Jahanshahi Gajar, Heat and Mass Transfer, Fundamentals and Applications, McGraw-Hill Education.